In this video, we'll talk about testing hypotheses about a single population parameter, or in other words, how do we go about conducting a t-test. So now recall that we could write the population model as the following. So we were trying to explain the variation in y using a bunch of explanatory variables. Now, assuming that our classical linear assumptions hold, we already know with the first four assumptions that if we use ordinary least square techniques, that we will produce an unbiased estimator of beta j. But we want to study or we want to test the hypothesis about that particular beta j. So if this is the population parameter, if I want to capture the effect of x1 on y, then I want to make some hypothesis about beta 1 because there is no way to know for us, there's no way for us to know what beta 1 is. So we have to hypothesize what that might be. So in order to do that, we have to test our hypothesis about some particular value of beta 1. Okay, so here we are just going to use beta j to denote the effect that any xj has on y. Okay, so this is just a more generic way of writing your slope coefficient, for instance. Okay, so under the classical linear model assumptions, we can write down what the t distribution is for our standardized estimators. So in the last video, we'd seen that this ratio was following a standard normal distribution. So here when we replace, so earlier we had sigma, which was unknown to us, but now we have sigma hat. If we replace sigma with sigma hat, which is an estimator that can vary across samples, this is going to take us from the standard normal distribution to the t distribution. So we're going to say that under the classical linear model assumptions, the first 6 assumptions, this standard normal random variable follows a t distribution, okay, after we made that replacement, okay? And this t distribution has n minus k minus 1 degrees of freedom. So you can write this as t degrees of freedom, or in other words here you can say degrees of freedom equals n minus k minus 1, right? So here this is just coming from the fact that we are estimating k plus 1 parameters, okay? So k slope coefficients and 1 intercept. So let's move on and try to understand what type of properties characterize the t distribution. So the t distribution also has a bell shape like the standard normal distribution, but it is a little bit more spread out than the standard normal distribution. So remember that the standard normal distribution has mean 0 and variance 1. Now, whenever degrees of freedom are greater than 1, which is not asking for much, right? So we're basically saying degrees of freedom equals n minus k minus 1. As long as this value is greater than 1, the expected value of this t statistic is equal to 0. Okay, and the variance of this t statistic that we defined previously, that ratio, is going to be equal to the ratio of the degrees of freedom divided by the degrees of freedom minus 2, okay? And so we can see for what happens when we take different values for degrees of freedom. For example, if degrees of freedom were 10, then we can calculate what the variance is, right? So in this case, we can say the variance for when degrees of freedom is 10 is basically 10 divided by 10 minus 2, which is 10 over 8, which is 1.25. Okay, and this is 25% larger. The variance is 25% larger than the standard normal variance, right? So you're basically comparing 1.25 versus 1, right? So this is the t distribution. This is in the standard normal. So standard normal case. But whenever, let's say you were taking a bigger sample, like hopefully you don't have such a small sample with just 10 degrees of freedom, you have many, many more hundreds or maybe millions of observations. If degrees of freedom is just 120, notice what happens to the variance of the t statistic. So the t statistic is just then 120 divided by 118, and this is equal to 1.017, okay, which is only 1.7% larger than the standard normal. So in other words, as your sample size increases, and becomes much, much, much bigger, or tends to infinity, then, so as n goes to infinity, your degrees of freedom are also going to go to infinity, okay? And so the t statistic is just going to follow a standard normal distribution in that case, okay? So remember that, the difference is practically small if degrees of freedom are greater than 120, because we already had that value 1.017 earlier for when degrees of freedom were 120. And we can take a look at a graph, for example, that compares the standard normal probability density function against a t distribution with just 6 degrees of freedom. Okay, so hopefully we don't have that. But you see that there's this nice bell shape also for the t distribution centered around 0. And the variance, right, the spread of the distribution varies a little bit. Of these two distributions varies a little bit. And you can see that the red line here, which is our t distribution, is a little more spread out than the standard normal. But these would really coincide if degrees of freedom were almost, coincide if degrees of freedom were greater than 120. So now that we understand the t distribution and the t statistic, we can use this result to test the null hypothesis about a particular xj and its effect on y. So whenever we are talking about the effect, remember that we are talking about partial effects. So here, if we are talking about a particular xj, the associated population parameter, or the effect of xj on y in the population, is captured by beta j. So we are hypothesizing here, we are setting up our null hypothesis. We are setting up our null hypothesis by saying that beta j has no effect, xj has no effect on y, okay, no partial effect on y, which is to basically say that beta j equals 0. So we are hypothesizing that this doesn't have an effect. So let's say here, let's take an example here. So let's say we have this example that we have been running with for the past few lectures, that if we were trying to explain the variation in log wage, we can explain that with level of education, experience, or tenure. Okay, so if we wanted to hypothesize what the effect of experience is on log wage, then we are talking about beta 2. So we could hypothesize that beta 2 equals 0, and this is how we set up our null hypothesis. Okay, it can be anything really, but 0 is capturing the fact that experience has no effect on log wage after we have controlled for education and tenure. In other words, that experience has no partial effect on y.